Alrighty, so here we go with some more related rates problems from our textbook. Number 18 from section 4.1. A baseball diamond problem. A baseball diamond is a square with sides 90 feet. A batter hits the ball and runs toward first base with a speed of 24 feet per second. At what rate is his distance from second base decreasing when he is halfway to first base? Okay, so here's the guy, here's the runner. He's running towards first base, and they want you to determine how fast his distance from second base is decreasing when he's halfway to first base. So you're looking at this distance, right? So again, what have we formed here? We formed a right triangle, right? Because since this is a square, this angle here would be a 90-degree angle. So I guess what I can do is I can label these things I don't know, A and C, right? Now you might say, well, what about B? B is a constant. This length here, right, from first base to second base is not going to change. It's always just going to be 90 feet. So what do we really know here? What is our relationship? We know that A squared plus 90 squared equals C squared, right? That's just our Pythagorean theorem. So what else do we know here? We know that he's running towards first base with a speed of 24 feet per second. So what ends up happening here is A, right, the distance from him to first base is actually getting smaller, right? It's decreasing 24 feet per second. So that's the only thing that's a little tricky here. Yes, he's running positive 24 feet per second, but we're looking at the distance from him to first base. So that distance is actually decreasing. So how fast is A changing? Right? dA dt is actually negative 24. Right? So we know dA dt is negative 24. And for part A, of course, we want to find how fast his distance from second base is decreasing. So in other words, we want to find dC dt when he's halfway to first base. So he's halfway to first base, he's going 45 feet, he has 45 feet left, so really when A equals 45. So what we can do is we can get C at this point just by using Pythagorean theorem. If we know that A is 45, right, just do 45 squared plus 90 squared equals C squared, right? Because C is changing. The only constant here is the 90. 90 is always going to stay the same, but A is getting smaller, C is getting smaller. So what is C when A is 90? I don't know. I'm using a calculator for this. So it would be, you would just go in and do the square root of 45 squared plus 90 squared, which is going to be 100.6. So C is roughly 100.6 feet. All right. And again, to find this now, we're going to use this equation and we're going to differentiate with respect to time. So when we differentiate with respect to time, we would have 2a dA dt plus 90 squared is really 1800, but again, it's a constant, so the derivative of a constant is just 0. And then c squared, that would become 2c dc dt, right? And as we saw in class, you can just cancel out these 2's, right? They divide out on both sides basically. So now just plug in the values. So we know A is 45, dA dt is negative 24, and this is equal to 100.6 times dc dt. So we're just going to do 45 times negative 24 and then divide by 100.6. So when we do that, dc dt, right, his distance from second base, it should also be negative, and it's going to be because we have one negative in this problem, right? So what we do is we just divide 45, oops, sorry, we just divide 45 times negative 24 by that answer there, which was 100.6 something. But I can use the answer button to get the more precise value in there. So if we divide 45 times negative 24 by 100.6, we will get negative 10.7. So dc dt in this case is negative 10.7 feet per second. So that would be how fast his distance from second base is changing, right? Because he's getting technically closer to second base as he's running towards first base. So negative 10.7 feet per second. And then moving on to part B. Part B is asking you at what rate is his distance from third base increasing at the same moment. So we're dealing still with the moment in time where he's halfway to first base. So, I mean, this picture isn't super accurate. He's a little bit closer to home, but we'll just use this in forming the triangle. So we're looking at his distance to, or distance from, third base. So we're looking at this distance here. And now in this case, I'm not going to use the same triangle I did before, because if I use this triangle here, you see that's no longer a right triangle, so then my Pythagorean theorem is not going to hold. So what I'm going to do is I'm going to be able to use this triangle, because it's really the same triangle, and that's why you'll see in a sec the answer is going to be the same, because we still have the same setup. This distance here from home to third is still 90 feet, right? Because all the distances are 90 feet because this is a square, right? And then again, you could still again call this C and call this A. All right. Now the only difference in this part B is, and I'm not going to go through the whole calculation because you'll see how it's going to work. My relationship here would still be the same Pythagorean theorem, right? It would still be a squared plus 90 squared equals c squared. So I'd still have this same Pythagorean theorem. The only difference is now my dA dt, look at the A, look at my A now. My A is no longer the distance from him to first. My A is the distance from home to him. So in this case, A is getting bigger. So the only way part B changes is now dA dt, since he's getting further away from home. So that A distance is increasing. This is now going to be a positive 24, right? But otherwise it's identical. So the only thing that's going to change in my problem, right, I would still have found C. So C is still going to be approximately 100.6, right? And I would still have the same relationship, right? A dA dt equals C dC dt. And again, the only difference now is the negative 24 would be a positive 24. And then when I divide by 100.6, I would end up with a positive 10.7 feet per second. So his distance from third base is actually increasing at the same rate as his distance from second base is decreasing. All right, so that's actually an interesting phenomenon there. Okay, so all that happens in part B really is one sign changes to positive, so then the result becomes positive. So it's positive 10.7 feet per second. So here's another related rates problem, number 20 from the textbook. A boat is being pulled into a dock by a rope that's attached to the bow of the boat. and it goes through a pulley on the dock that's 1 meter higher than the bow of the boat. So what you can see you're forming there again is going to be a right triangle. I'm going to not use the highlighter because it's too thick. I'm going to use this just pen. Well, this is not a good drawing at all. You know what? Do it this way. Can I insert just a line here? Let's see. Yeah, just make it thicker. And then we got this. Good enough, right? So there's your right triangle. Took me long enough, but I got it. Right, so there's the right triangle. So let's see what's happening here. This distance is definitely changing, right? Because he's getting closer to the dock. This distance is definitely changing because the pulley is being pulled in, right, as the boat moves closer to the dock. The only thing that's not going to change is this height here, which is always going to be 1, because it says that's 1 meter higher than the bow of the boat, right? So there's from the bow to down there, and then up 1 meter to get to where the pulley is. So that's always 1, and then we can call this again like we did in the last problem A, and this here C. So they want you to find how fast the boat is approaching the dock. So how fast it's moving in this way. So in other words, you're asked to find here dA dt when the boat is 8 meters from the dock. So in other words, when A equals 8, right? So you want to find dA dt when A equals 8. And you also know that the rope is pulled in at a rate of 1 meter per second. So the pulley is basically being pulled in, right? This rope here is being pulled in at a rate of 1 meter per second. So that's how C is changing, right? So dC dt is getting smaller, right? So it's going to be negative, and it's 1 meter per second, so it's negative 1. So dC dt is negative 1. So now what do I know? Again, I have Pythagorean theorem. I know that a squared plus 1 squared equals c squared, right? So a squared plus 1 equals c squared. And then again, take the derivative, and I would have 2a dA dt equals 2c dc dt, but again, the 2's will cancel, so I'll just have a dA dt equals c dc dt. And in this case, I'm trying to find dA dt. So I know what a is, right? A is 8. I know what dc dt is. It's negative 1. The only thing I don't know is c, but of course I can find c by the Pythagorean theorem. So when a is 8, I have 8 squared plus 1 squared equals c squared. So I have 65 equals c squared. So c is going to be the square root of 65. Right? So c is the square root of 65. So I can just plug that in as such, I guess. So I would have 8 dA dt equals the square root of 65 times dc dt, which is negative 1. So just negative square root of 65. So I know dA dt, if I just divide both sides by 8, I'll end up with negative square root 65, right? So negative, oops, sorry, negative, got ahead of myself there. I was going to do the second for the square root. So negative square root of 65 divided by 8, negative 1, basically negative 1, we'll say. Well, but see, we want to differentiate it, I guess, a little bit from the rate of the pulley. So maybe I will actually go to like 4 decimal places. Negative 1.0078. negative 1.0078 feet per, nope, it's meters per second, sorry. Not feet per second, meters per second. So that one's being pulled in at a rate of negative 1.0078 meters per second. So that would be your dA dt. All right, so we've reached our last one, number 25, which is the most complicated one here because it's going to involve two steps. So we're going to actually have to do two separate calculations, two separate equations to get our final answer here, right? So we've got these carts that are connected by a rope 39 feet long. So the total length of that rope is 39 feet. And it passes over a pulley, and there's a point Q that's on the ground, I guess, 12 feet directly beneath P and between the carts. So that's really the one thing that I guess is not going to be changing here. That's always 12 feet from the pulley down to the floor. Cart A is being pulled away from Q, so you see the arrow here, at a speed of 2 feet per second, and they want to find how fast B is moving toward Q. So in other words, they want you to find this. When cart A is 5 feet from Q. Okay, so let's give these things labels, I guess. So we'll call the distance from Q to cart A, A, and the distance from Q to cart B, B. That distance is always 12. And now here's the little catch here, right? This rope has a total length of 39 feet. So if I just call this segment here X, let's say, right, that forces this segment over here to be the remainder. So if the whole thing is 39 feet, this is going to be 39 minus X, right? Because you see what the problem is here. If I look at this whole big triangle, right, it's not a right triangle. Okay? So you're going to have two separate calculations here. So what we're going to do first we're going to use this left-hand right triangle and say, all right, well, I know that a squared plus 12 squared equals x squared, right? So I know a squared plus 12 squared equals x squared. And you always need an equation that's going to relate the quantities, right? If you don't have that, then you're beat. So this is really kind of like our starting point. Get the equation that relates the quantities. And what do I know? I know that cart A is being pulled away from Q at a speed of 2 feet per second. So in other words, A is getting bigger. So dA dt is increasing, right? dA dt is the change in A, right? So A is increasing 2 feet per second. So dA dt is 2. So if I know a squared plus 12 squared equals x squared, and my goal really here is going to be to find dB dt, right? But if you notice, b is not even in this equation, so I'm going to have to hold off on this for a second, right? So my goal is to find dB dt when a equals 5, right? When cart A is 5 feet from Q, so when A is 5. So again, do the derivative as we did in the last problem. I'm going to have A dA dt equals x dx dt. And I know that A is 5, and I know dA dt is 2. So what is x when A is 5? I would just use my Pythagorean theorem, but the nice thing is this is then going to be a 5, 12, 13. So when A is 5, that means that x is going to equal 13. So it makes this nice. So I know x is 13, A is 5, dA dt is 2. So I have 5 times 2 equals 13 dx dt. So what is dx dt going to be? It's going to be 10 divided by 13. So it's 10/13ths, right? What is this measured in? Feet per second. So dx dt is 10 13 feet per second. And now think about this. There's a couple of different ways to now look at this. You know that this is all attached, right? This rope, this is one rope. So if x is getting bigger at a rate of 10 13 feet per second, that means that this remaining portion of the rope is actually getting smaller at the same rate. So we know that the derivative here of 39 minus x with respect to time is actually going to be negative 10 13. Okay? And if you don't buy that, what you can actually do, and this is kind of a nice thing, is you can just say, all right, well, what is the derivative with respect to t of 39 minus x? It's just the derivative with respect to t of 39, which is just 0, minus the derivative with respect to t of x. And this is just dx dt, right? So you just end up with the opposite of dx dt, which is just negative 10 13. Because now I'm going to use this in my right-hand triangle now. So now I'm going to look at my right-hand triangle and say, all right, well, I know that when x equals 13, that then means that 39 minus x is going to be 39 minus 13, which is going to be 26. And I know that this other leg is always 12, so I can find b, right? So I have the hypotenuse is 26. I have one leg here, which is 12, and I can find the other leg b by using Pythagorean theorem. So I would just say 12 squared plus b squared equals 26 squared. So b squared is going to be 26 squared minus 12 squared. I'm going to have to do this on the calculator, right? So 26 squared minus 12 squared gives you 532, and then just take the square root of that. So b is going to be the square root of 532. So I need that, right? Because now when I'm using my right-hand triangle, my equation would be 12 squared plus b squared equals technically 39 minus x squared, right? But then when I take the derivative with respect to t again, this just becomes b db dt equals, what I could do to make this simple here is I could just call 39 minus x y, right? So it's really equal to y dy dt, right? But again, dy dt is just going to be the opposite of dx dt. So now this b is really square root of 532. db dt is what I'm trying to find, so finally I can find it now. And this is equal to y, which was 39 minus x, so it's really 26, times dy dt, which was just the opposite of dx dt, which is negative 10 13. So we would just have this here where we would do negative 20 divided by radical 532. So we did end up with db dt equals negative 20 divided by radical 532, which is going to give me negative 0.867 feet per second. And of course that's negative because that distance there, b, is getting smaller. All right, so that would be some more related rate problems.